The strategy I suggested was to take the first two equations and eliminate a variable. Take the last two equations and eliminate the same variable. That will give you two equations and just two variables, which then you can solve. But you got to have a strategy. Like your goal is to eliminate one of the three variables to solve it. All of that said, do you have to do that every time? Certainly not. Don't look a gift horse in the mouth. Like, I don't think that means anything to us anymore. Who has a horse? Who's gifting the horse? Why do we even say this? I don't know. Something about horse dentistry, I guess, but I'm sure some of you could explain it to me. Wait a minute, we got no animal husbandry people in here, do we? You guys are just about, oh yeah? Oh.
My mother works with horses.
Your mother works with horses? Ah. She retired? Oh. Tired? You ask her if she's tired of horsing around? Sorry, that's really horrible. I'm sorry about making a joke about your mom. But seems like it happened. All right, I feel like this conversation could diverge somewhere. Let's not go there. Okay, so that was unexpected. Cool. Look, this one is easier because, like the last equation, already has z isolated, right? So you have z. Z is 3. Yay. And then once you see that, look at the next one. The next one, the next to last one, has only y and z in it, right? So put that 3 into there, and then you've got an equation just in y. That means then you know what y is. Then you can go back to the first equation and solve for x. So look for things like that. If you find some kind of nice pattern like that, don't insist on using my algorithm for solving 3 equations, 3 unknowns, because sometimes it's easier. I think the next problem is genuinely intertwangled. Like this one, it's not nice like the one before. So what I did here was I added equations 2 and 3. It gave me, oh, that one's nice. Also look for that. If you can somehow add equations to make 2 variables cancel, that's huge. Anyway, so I would encourage you, if you're not already solid on solving 3 equations and 3 unknowns, then work some more. So how do we complete the square? I hope by now you know. If you don't, it's not too late. You can learn it, right? So if we have a quadratic, how does it factor? There are 3 cases, right? Either it factors in distinct real factors, it's a repeated factor, or it's prime. We discover this in completing the square. By when we complete the square, we have the square minus a number. If that's the case, that means it factors over the reals. If we complete the square and we just have the square, well, it's repeated. If we complete the square and we have the square plus a number, that means it's prime. These are the 3 cases. This is what we've seen over and over and over again. And here those 3 cases present themselves. Right? This one, I complete the square. I have a negative, so that means it factors. It's not pretty, but it factors. This one, I complete the square. I've got a negative. That means it factors. It's not pretty, but it factors. This one, I complete the square, and oh, completing the square actually factored this one. That's kind of funny, right? So this one here, notice the instructions, factor over c. If I don't say over c, then you don't have to factor this one, right? If I say factor over the reals, if I said factor x squared plus 4x minus 7 over the reals, oh, you could still do it, right? Because that would be this. That's factored over the real numbers. Square root of 11 isn't a real number. How about this one? 2x squared plus 3x. So first of all, that 2, factor the 2 out, right? Get x squared isolated like that. Then I complete the square. X plus half of that's 3/4. I subtract 9/16 from 2. Well, 2 is 32/16, so we end up with a square plus something, right? If we were just factoring over the reals, we'd be done here because this is prime. But since we're using complex numbers, we can pull that, we can rewrite that as I times root 23 over 4 minus I times root 23 over 4. So like that. Any questions about all this? Anyway, I have the complete solution for the mission sitting there for you to look at. Let's see if there's anything else I want to talk about here before you head out. Look for difference of squares. Difference of squares is easy if you know about it, but it's, like this, x squared minus 11 is x plus root 11 times x minus root 11. Let this not be a mystery to you. Learn this pattern. Likewise here, 6x squared minus 7 is the square root of 6 times x, quantity squared, minus the square root of 7 squared. So again, this is the pattern, a squared minus b squared, which is a plus b times a minus b. Again, the same pattern. Sometimes we have something like this, right? How do you do this one? You could complete the square and do it that way. I don't recommend that. For this one, I would start by trying a template like 2x and 3x and trying putting numbers in and see if it can work, Unless I'm just a jerk, it's probably going to work out like that, right? There's a prime one. Sometimes students forget this. This is a really bad thing to forget on the test. This is one of the first things we do in factoring is look for a common x or a common power of x throughout the polynomial, right? Don't forget about this. This matters. Because if you don't think about this, how would you do that? Like, I'm not sure what, I guess you could complete the square, but that's so needless here because we just factor x out and we've got x plus 2. Now I factored a half out first just to make life more natural. I could have just factored the x out and had, x times 1/2 x plus 1. I could have done that, right? So there's that. What's this? What's going on here? What's this? What am I doing? Going from there to there. How did that go? What did I do? What magic is this? Nobody? Note to self, put that one on test. All right, no. So that, again, it's a squared minus b squared. A plus b, a minus b, yeah? That's the pattern. That's all I did. Just think of this right here as a, that as b, a squared minus b squared, a plus b, a minus b. And that goes back to that. Let's see here. It's good to know the quadratic formula. It's better to know how to derive the quadratic formula. It's better to know about solving with the square root property like we're doing here, right? You don't have to go back to the quadratic formula. If you understand square root property, we can solve these like so. That said, I do on occasion use the quadratic formula, and it's not bad for you to do that. But if you do that, I do expect you to simplify your answer and not just leave it as a mess for me to try to interpret, okay? Otherwise, I will take off some credit. I guess the other thing we talked about was how to graph a parabola. That will likely be on the test. How do you find the vertex? How do you find the x-intercepts? What's the y-intercept? Can you graph a parabola? Sometimes I ask the question in the format, here are pictures of parabola, which is the play match game, right? Here's like 4 parabolas, match it to 4 formulas. Like that's a good way for me to ask this question because then I don't have to try to interpret your graphs, which is sometimes unhappy for me. Yes, sir. If I could solve world hunger, but never complete a square, never be allowed to complete a square again. Oh. Well, I just, people would have to say hungry, I guess. Because a world without completing the square is a world without math. What a great question. Very funny. Sorry, let me get this out of the way here.